Debye Huckel equation. We know strong electrolytes are almost completely ionized in solution. That means their degree of ionization is almost unity for all concentrations. But it can be shown experimentally that their equivalent conductance or molar conductance increases gradually with dilution. In order to explain this abnormal behavior of strong electrolytes, Debye Huckel and Onsager in 1926 put forward the modern theory of strong electrolytes, that is known as Debye Huckel-Onsager theory of strong electrolytes. Let me recall that in the case of weak electrolytes, the increase in molar conductance or equivalent conductance on dilution is due to increase in degree of ionization. In the case of strong electrolytes, there is some inter-ionic attractions, especially at higher concentration. So when it is diluted, the ions become far apart, so the inter-ionic attraction decreases and the ionic mobility increases. So Debye and Huckel, they suggested that the increase in equivalent conductance on dilution of strong electrolytes is due to decrease in inter-ionic attraction. And there are two important effects involved in inter-ionic attractions. They are relaxation effect and electrophoretic effect. Let us see what is meant by relaxation effect first. If you consider an ion in solution, it will be surrounded by number of ions of opposite charge, and that is known as the ionic atmosphere. And in the absence of electric field, this ionic atmosphere will be symmetrical. You can see in this figure, in the absence of electric field, the central cation that is surrounded by a number of anions, and this ionic atmosphere is symmetrical. But if you apply an electric field, what happens is the central positive ion migrates towards the cathode and the anions migrate towards the anode. As a result, what happens is the symmetric ionic atmosphere gets changed to an elliptical atmosphere. The shape of the atmosphere, symmetric atmosphere, will be lost. And in order to regain or rebuild the symmetric atmosphere, it takes a definite time. And this time is known as the relaxation time. And the net result is that the central positive ion experiences a retarding force from the counter ions, and this results in reduction in the mobility of the central ion and the conductance of the solution decreases. This effect is known as asymmetric effect or relaxation effect. It is known as asymmetry effect because as a result of application of electric field, the symmetric atmosphere is lost, and it is called relaxation effect because of the relaxation time. That is the definite time that is required for rebuilding of another symmetric ionic atmosphere. Now, again, in this picture, you can see the central positive ion. And you know, if the solvent is water, there will be hydration. Hydration means the positive ion will be surrounded by a number of water molecules in such a way that the oxygen will be pointing towards the cation, and that is known as hydration. So here what is happening is, when the central positive ion migrates towards the cathode, the anions along with the solvent cage migrates towards the anode. So cation along with its solvent cage moves towards the cathode, while the anions along with the solvent move towards the anode. This results, or there is counter movement of the ion along with the solvent. This also results in decrease in the speed of the ions. So electrophoretic effect reduces the mobility of the ions. And these two effects slows down moving ion. And this electrophoretic effect that depends on the viscosity of the medium. Also, the mobility of the ion depends upon dielectric constant as well as temperature. So on dilution, these inter-ionic effects weaken and the mobility of the ions increases, because on dilution the ions become far apart, they move apart, so that the inter-ionic effect decreases. And Debye, Huckel and Onsager worked on this relaxation effect and electrophoretic effect, and they put forward an equation, and that is known as Debye Huckel equation. Mathematically, it is lambda C, that is equivalent conductance or molar conductance at a particular concentration that is less than the equivalent conductance at infinite dilution lambda 0 by this value. And the first term, where D is the dielectric constant, T temperature, eta viscosity of the medium. So this first term corresponds to electrophoretic effect, and the second term corresponds to the asymmetry effect. So this is Debye Huckel Onsager equation. Lambda C is the equivalent conductance at a particular concentration, lambda 0 equivalent conductance at infinite dilution, D dielectric constant, eta viscosity of the medium, C concentration of the solution. And for a given solvent at a particular temperature, this expression can be written like this: lambda C equals lambda 0 minus A plus B into lambda 0 into square root of C, where A and B are constants for a given solvent. And this Onsager equation can be tested by plotting lambda C against square root of C. So if you plot lambda C against square root of C, it can be seen that in the case of strong electrolytes, there is gradual increase. And this dotted line represents the theoretical, that is based on the equation, Debye Huckel equation. This is theoretical and this is experimental. For example, in the case of KCl. So we can see the theoretical and experimental plots are agreeing, especially for lower concentration, and at higher concentration there is some deviation. Whereas in the case of, and this is applicable in the case of univalent ions, but in the case of polyvalent ions, it is seen that at higher concentration there is marked deviation.